Right then, let's get straight into it. Imagine you're sitting down, maybe for your computer science GCSE work, trying to tell a computer what to do. You type in some instructions, seems obvious to you, maybe it's a bit like English, but the computer, um, it's completely lost, isn't it? At first, anyway.
That's spot on.
Yeah.
Yeah, computers fundamentally operate using a very basic language, binary code,
Mm.
just strings of zeros and ones. So the big question really is, how do the instructions we write in a way that makes sense to us actually get turned into those zeros and ones the computer understands?
Exactly. And that's what we're digging into today. In this deep dive, we're going to unpack programming languages and these really important tools called translators.
They're the vital link.
Yeah, the link between us, the programmers, and the computer's brain, the processor. We'll look at the different types, mainly focusing on that big divide, low-level and high-level languages.
But honestly, getting your head around this difference and how these languages get converted, it's fundamental.
Hmm.
Really core stuff for your GCSE, definitely.
Okay, so let's start right down low then. Low-level languages. Now, the key thing here is they're closer to how the computer actually works, right?
That's precisely. They have a very direct connection to the computer's hardware. They essentially translate almost directly into machine code,
Those zeros and ones we mentioned?
the very same, the stuff the processor actually understands.
And the earliest type, the very first generation, that was
Yeah.
machine code itself. People actually wrote in zeros and ones.
They did. Can you imagine? Directly inputting endless lines of binary. It was incredibly slow, really complex, even for simple tasks.
Wow.
Yeah, early programmers had to manually punch these in or flip switches. It took ages, was super prone to errors, and you needed this incredibly deep knowledge of the computer's guts, you know.
Blimey. Okay, so think of machine code like the raw on-off electrical signals.
That's a good way to think about it, yeah.
Yeah.
0 for off, 1 for on, in those billions of tiny switches inside the chip.
Thankfully, things moved on a bit then. Second generation.
Yes, assembly code. This is where things became, well, slightly more human-readable. Still low level, but a step up.
How so?
It introduced mnemonics. Think of them as little abbreviations, short codes, like LDA for load accumulator or STA for store accumulator.
Ah, okay. So instead of 011, 01011, you might write LDA.
Exactly. These mnemonics stand for specific machine code instructions. Makes the code a bit easier for us humans to read and write compared to just pure binary.
But it's still a very direct link. One assembly instruction pretty much equals one machine code instruction.
Ah, that's the crucial point, yes. Almost always a one-to-one relationship. But, and this is important, the processor still can't run assembly code directly.
Ah, okay. It still needs translating.
It does, and that translation is done by a specific program called an assembler.
Right, so the assembler takes the assembly code with its mnemonics and turns it back into the raw zeros and ones. Got it. Now, why bother? What are the upsides of working at this low level, particularly thinking about GCSE or beyond?
Well, the big advantage is control. You get incredibly fine-grained control over the computer system, its memory. Special little storage spots in the processor called registers, the hardware itself.
Registers, like super fast little scratch pads inside the processor.
Exactly like that. Controlling them directly can really speed things up. Because you're so close to the metal, programs written in low-level languages can often be very, very efficient. Less memory, faster execution.
And you can talk directly to hardware bits.
Yeah, if you need to control specific sensors or devices directly, sometimes low-level is the only practical way. Think about the code controlling, say, the vibration motor in your phone. That might well be low-level.
Okay, so speed, efficiency, direct hardware control, big wins. But I'm sensing some major downsides, too.
Oh, absolutely. The biggest one is probably just how difficult it is to write and understand compared to other languages. It's
Yeah.
not intuitive. And because it's tied so closely to the hardware, code written for one type of processor, say an Intel one, probably won't run on a different type, like an ARM processor in your phone. It's machine dependent.
So not portable.
Not really. Plus, it's much easier to make mistakes, errors that can be hard to find.
Mm.
And like we said with machine code, you really need to understand the computer's architecture in detail.
Okay, so powerful but tricky and very specific. Makes sense. Right, let's shift gears then. Let's talk about the languages most of us, especially doing GCSE Computer Science, are more likely to actually use or see high-level languages.
Exactly. High-level languages are designed to be much closer to human language. They use English-like words, mathematical notation. They're just generally easier to read, write, and understand.
Less like cryptic codes, more like instructions you could almost follow yourself.
Pretty much. That makes them way more accessible for learning, for debugging, for working in teams.
And I guess most modern software apps, games, websites is written in these high-level languages.
The vast majority, yes. Things like Python, Java, C Sharp, JavaScript. These are all high level. The benefits in terms of development speed and maintainability usually outweigh any potential performance loss compared to low level.
You mentioned performance. It's interesting how faster computers actually allowed these easier languages to become common, isn't it?
That's a really key point. As processors got faster and memory got cheaper and bigger, we didn't need to squeeze every last drop of performance out by writing complex, low-level code for everything.
So we could afford the sort of overhead of languages that were easier for humans.
Precisely. We traded a bit of raw machine efficiency for a huge gain in programmer efficiency and productivity, a worthwhile trade-off most of the time.
And crucially, with high-level languages, one line I write might actually do a lot underneath, right? It translates into many machine code instructions.
Spot on. A single line like print, hello, in Python involves many steps at the machine level. This is a much more abstract relationship than the one-to-one of assembly.
But just like assembly, these high-level languages still need translating before the processor understands them.
Absolutely. The computer only understands machine code. So Python, Java, whatever. It all needs to be translated somehow.
And we're talking about languages GCSE students will definitely recognize. Python is huge now, isn't it?
Oh yeah, Python's massive. Java's still very important too. Even visual block-based languages like Scratch are conceptually high-level Kirk. They just use a different interface before getting translated.
So let's summarize the advantages of high-level languages again. Easier to read and write?
Definitely. Much quicker to develop things.
Yeah.
Easier to debug too. Finding errors is usually more straightforward.
And you mentioned portability.
Yes, a big one. Often, high-level code can run on different types of computers, different operating systems, with few or no changes. That's huge.
And one line does more.
Yep. Higher level of abstraction means more power per line of code you write.
Okay, sounds great. Easier, more flexible, portable. What are the downsides then? The trade-offs?
Well, the main one is you lose that direct, fine-grained control over the hardware that you get with low-level languages. You're working at a higher level of abstraction.
So you can't easily fiddle with specific memory addresses or registers.
Not usually, no. The language and its translator handle a lot of that for you. Also, that translation step has to happen, which adds a layer.
And does that translation mean they might be a bit slower or use more memory sometimes?
Potentially, yes. Compared to highly optimized low-level code for the exact same task, a high-level program might be slightly less efficient. Though modern translators are very good, so the gap isn't always as big as it used to be. For many apps, it's negligible.
Right, so it's a balance. Ease of use versus potential peak performance and direct control. Really important distinction for GCSE. Okay, we've got low level near the hardware, high level closer to us humans. But the key thing linking them is translation. Let's dive into the translators themselves.
Good idea. So a translator in this context is simply a program. Its job is to take the source code, the stuff the programmer writes, and convert it into machine code.
The zeros and ones a processor can actually run.
Exactly. Without a translator, your Python script or your assembly code is just a text file the computer can't do anything with.
And we know there are different types. We mentioned the assembler already for assembly language, right?
We did. An assembler translates assembly language into machine code. Remember that near one-to-one relationship between assembly mnemonics and machine instructions. The assembler handles that conversion.
Takes LDA and turns it into the right binary sequence.
Precisely. Each assembly line typically becomes one machine code instruction.
And you said assemblers aren't used as much now, mostly for specialist stuff?
Generally, yes, because high-level languages are usually easier and faster to develop in. But assemblers are still vital for things like operating system kernels, device drivers, embedded systems, anywhere that extreme performance or direct hardware access is paramount.
What are the pros of using an assembler in those cases? Speed.
Speed is a big one, yes. You can potentially write highly optimized code. Also, the original source code isn't directly readable like a high-level language might be, offering a slight layer of obscurity, but that's rarely the main goal.
And the cons are basically the cons of assembly language itself. Hard to write, not portable.
Exactly. Difficult commands, changes mean reassembling everything, and it's tied to a specific processor architecture.
Right, so assemblers handle that specific low-level translation. Now, for the high-level languages like Python or Java that students are learning, we have two main types of translators, compilers and interpreters. Let's tackle compilers first. How do they work?
Okay, a compiler takes your entire high-level program, all the source code you've written, and translates it all in one go into machine code.
The whole thing at once.
The whole thing. It reads everything, analyzes it, checks for certain types of errors, and if everything's okay, it produces a complete machine code version of your program.
And this machine code version, is that something you can just run directly, like an .exe file on Windows?
Often, yes. A key feature of compilers is that they typically create a standalone executable file. This file contains the machine code and can be run on a compatible computer without needing the original source code or the compiler software itself.
That sounds quite efficient for distributing software. But what if there are mistakes in my code when I try to compile it?
Good question. If the compiler finds syntax errors like you've misspelled a command or used incorrect grammar according to the language rules, it will usually stop the process.
It won't create the executable.
Nope. It'll report a list of errors it found, telling you the line numbers where it thinks the problems are. You then have to go back to your source code, fix those errors, and then run the compiler again on the whole program.
So fix, recompile everything, test again.
Exactly. That's the cycle with compilers. But the upside is, once it is compiled successfully, that executable file usually runs very quickly because it's already pure machine code.
And compilers can sometimes make the code run even faster. Optimize it.
Yes. Many compilers perform complex optimizations during the translation process, rearranging instructions or finding cleverer ways to do things to make the final machine code more efficient in terms of speed or size.
Okay, so compilers. Translate everything up front, create a potentially fast executable, but need a full recompile after changes. Got it. What are the other type? Interpreters. How are they different?
Interpreters work very differently. Instead of translating the whole program at once, an interpreter translates and executes your high-level code one line or one statement at a time.
One line at a time, as the program is running.
Yes, exactly. It reads a line, figures out what it means, translates it, often into an intermediate form or by calling pre-existing machine code routines, executes that instruction, then moves to the next line, reads it, translates it, executes it, and so on.
So it doesn't create a separate executable file beforehand?
No, it doesn't. The interpreter software itself needs to be present on the computer every time you want to run the code. It's doing the translation live as the program runs.
What happens if it finds an error then?
If the interpreter encounters an error on a line, maybe a syntax error, or trying to divide by zero, it stops execution right there and then. It tells you about the error on that specific line.
Ah, okay. So you find out about the first error immediately when you run the code.
Precisely. This makes interpreters really useful during development and debugging. You run your code, it hits a bug, stops, you fix that bug, run it again, and see if it gets further. It's a much more immediate feedback loop than compiling the whole thing.
That sounds really handy for learning and testing, especially for GCSE projects.
Absolutely. It's often why languages like Python, which are commonly interpreted, are popular for beginners. That immediate feedback is great. Interpreters also tend to use less memory, less RAM, during the process compared to some compilers.
But there must be a downside. If it's translating every line, every time, is it slower?
That's generally the main drawback, yes. Because the translation is happening during runtime, interpreted code typically executes more slowly than equivalent code that has been compiled into machine code beforehand.
Every loop, every function call, it's retranslating.
Often, yes, or at least reinterpreting in intermediate form. This overhead means slower performance overall. Also, there's usually less scope for the kind of deep optimizations a compiler can do when it sees the whole program at once.
And distributing the code is harder because the user needs the interpreter installed.
Correct. You can't just give someone an executable file. They need the right interpreter installed on their machine to run your script.
Okay, so interpreters. Line-by-line translation and execution, great for debugging and development, stops on first error, but generally slower execution and needs the interpreter present.
You've got it. Compilers and interpreters, two different strategies for tackling that same fundamental problem of translating high-level code.
Right, so we've covered assemblers for low-level, compilers and interpreters for high-level, crucial concepts for GCSE Computer Science. Just to circle back quickly, why is any translation needed again?
It all comes down to the processor. The CPU at the heart of the computer is, fundamentally, quite simple in what it understands. It only gets machine code, those raw sequences of zeros and ones representing basic operations like add, move data, compare values.
So are human-friendly languages, Python, Java, even assembly, they're just meaningless text to the processor?
Until they're translated, yes. They need to be converted into that specific binary language the processor was built to understand before any instructions can actually be carried out.
Makes sense. And just to nail those key differences between compilers and interpreters for revision.
Okay, key difference one. Compilers translate the entire program to machine code before execution, often creating an executable file. Interpreters translate and execute line by line during execution.
Got it. And errors.
Compilers usually find all syntax errors during the compilation phase and report them together. You fix them all, then recompile. Interpreters stop execution at the first error they encounter during runtime.
Perfect summary. Definitely stuff to remember for exams. So, to wrap things up then, we've taken a pretty good look through the world of programming languages, from the really low-level stuff, talking directly to the hardware,
Machine code, assembly.
all the way up to the high-level languages like Python that let us write programs more easily. And we've seen how absolutely vital those translators are, assemblers, compilers, interpreters.
They're the essential bridge, aren't they? Making our ideas understandable to the silicon.
Absolutely. Understanding this hierarchy, low-level, high-level, and the translators, it's just, well, it's fundamental for anyone curious about how computers work, and obviously crucial if you're learning to program for your GCSE.
It really gives you that foundation. You start to see how the software you use actually comes to life.
And, thinking about how quickly things change, programming languages are always evolving. It makes you wonder, doesn't it? How might that translation process change in the future?
That's a great question.
Will we get even smarter translators? Or maybe completely new types of languages that blur the lines even more? What's next for how we talk to computers?
It's constantly evolving. Perhaps more AI involved in translation or optimization, who knows? But understanding the basics we've talked about today gives you the grounding to follow those developments. It's a fascinating area.
Definitely something to mull over.
Mm.
Well, that's all we've got time for in this deep dive. Until the next one, keep digging into computer science.